Hello everyone, welcome to chemistry class. Today's topic of discussion will be hydrogen peroxide, one of the most important compounds of hydrogen. So let's start with hydrogen peroxide. So the heading for today's discussion is hydrogen peroxide. Molecular formula of this compound is H2O2. This is the molecular formula of this compound. We will discuss the general methods of preparation of this hydrogen peroxide, then its structure in various physical states, its physical properties, chemical properties, and its important uses. So to begin with, we'll start with the general methods of preparation. Preparation of hydrogen peroxide. Now normally look at this. Hydrogen peroxide is prepared from metal peroxides. So alkali metal and alkaline earth metal forms stable peroxides. So we can start from this solid stable metallic peroxides. When we acidify these peroxides, this gives you hydrogen peroxide. So first one is from sodium peroxide, which is a stable solid. Now we take this sodium peroxide. This sodium peroxide is acidified with sulfuric acid. We take this cold sulfuric acid. When this gives you sodium sulfate plus hydrogen peroxide is formed. So we obtain this hydrogen peroxide from sodium peroxide acidification with cold ice called sulfuric acid. Now this method of preparation of hydrogen peroxide by acidification of sodium peroxide is known as Mark's method. So we can obtain hydrogen peroxide from sodium peroxide by acidification. Similarly, we can also obtain this hydrogen peroxide by acidification of barium peroxide. So we take this barium peroxide. Again, this is solid. Now this barium peroxide we acidified with cold sulfuric acid. Again we are taking this ice cold sulfuric acid. When barium sulfate insoluble precipitate is obtained plus hydrogen peroxide liquid is obtained, which is further distilled to obtain pure hydrogen peroxide. Now this preparation of hydrogen peroxide from barium peroxide solid, this is known as Thénard's process. Thénard's process. So simply saying, we can obtain hydrogen peroxide by acidification of metal peroxide. Then we can also prepare this by electrolysis. Electrolysis of sulfuric acid. Electrolysis of sulfuric acid. Dilute sulfuric acid. Now we electrolyze this concentrated sulfuric acid. Now we take this sample of sulfuric acid H2SO4. This is electrolyzed, means we carry out this process in a cell. We take this sulfuric acid, we pass electric current through the electrodes, then electrolysis reaction takes place, and after this electrolysis we get this H2O8, that is peroxodisulfuric acid. Peroxodisulfuric acid. Now this peroxodisulfuric acid is diluted H2 H2O8. When this is made to react with water, this gives you sulfuric acid plus hydrogen peroxide is obtained. So first what we do is we take a sulfuric acid sample. To this we pass electric current through electrodes, means through an electrolytic cell. When this sulfuric acid is electrolyzed, oxidized to give you peroxodisulfuric acid. Now this peroxodisulfuric acid on dilution with water gives you sulfuric acid and hydrogen peroxide. From this we concentrated hydrogen peroxide. So this is one of the methods by which we can prepare hydrogen peroxide in bulk. Then there is a very important process, that is auto-oxidation of 2-ethyl anthraquinol. We take this particular compound 2-ethyl anthraquinol, that is, this is the compound. This is aromatic ring. We have this compound C2H5. Now this is what they call as 2-ethyl anthraquinol. This position is known as 2 position. This is known as anthraquinol. Now this anthraquinol is oxidized in presence of air. That is, we have oxygen present in the air. Now in presence of this oxygen, that is aerial oxidation, when this is oxidized to give you anthraquinone and hydrogen peroxide is formed. 2-ethyl anthraquinone plus hydrogen peroxide is formed. This is a method which is used in industrial scale for large scale production of hydrogen peroxide. Why? Because the reagent used for this reaction is aerial oxygen, which is available in large quantity, and this is also economical. So we take this ethyl anthraquinol, we pass this air, that is aerial oxidation, it automatically oxidizes to give you hydrogen peroxide and 2-ethyl anthraquinone. This is 2-ethyl anthraquinone is formed. Again, this 2-ethyl anthraquinone reduced in presence of hydrogen palladium, then again this gives you anthraquinone. Means after formation of this 2-ethyl anthraquinone, means this is oxidized form, this is reduced form. We can again regenerate this reduced form for further aerial oxidation by treatment with hydrogen in presence of palladium. So these are some of the common methods by which we can prepare hydrogen peroxide in small scale or in large scale. So this is the preparation of the hydrogen peroxide. Now coming to the structure of this hydrogen peroxide. Now this hydrogen peroxide can exist in gaseous phase or in liquid or solid phase. In both the case, gaseous phase or liquid or solid phase, this exists in the form of open book structure. This way, open book structure. That means the plane of, look at this HOO and this OOH, these are in two different planes. Suppose we take this, the plane, this is another plane. Now in the gas phase, this bond means this is one plane, that is hydrogen oxygen oxygen plane. This is another plane, hydrogen oxygen oxygen plane. The angle between this plane, that is what we call as dihedral angle between the plane, this angle is 111.5, that is in gaseous phase, and this angle OOH, this bond angle in this molecule is 94.8 degree. Same, we have hydrogen, oxygen. Oxygen bond angle is 94.8. The bond distance between these two oxygen, that is 1.48 angstrom, and this bond distance between this hydrogen oxygen bond length, that is 95 picometer. This is the characteristics of this molecule, that is hydrogen peroxide, in gaseous phase. Now in liquid and this solid phase, there is extensive hydrogen bond. Because of this extensive hydrogen bond in solid or in gas liquid state, there appears to be slight changes in the dihedral angle, that is angle between the plane. This was 111.5 in gaseous phase. Now in solid phase, this dihedral angle between the plane is 92.2. That is, dihedral angle is decreased. This decrease in dihedral angle, this is due to hydrogen bond. Due to hydrogen bond. So because of this extensive hydrogen bond, dihedral decreases from 111.5 to 90.2 degree. Now when the dihedral angle is decreased to 90.2 degree, then this angle, OOH bond angle, this increases to 101.9 degree from 94.8. So this OOH bond angle is more in case of solid phase, less in case of gaseous phase. The bond length, oxygen bond length, is approximately same, that is 1.48 in case of gas phase, this is 1.46 in case of solid state. And this bond length, that is OH bond length, which was 95 picometer in case of gaseous state, now this increases to 98.8 picometer. So this is the characteristics of this structure. So what is important is this exists in the form of open book structure, and OOH, these are in two different planes, and the angle between this plane is what we call as dihedral. So in case of solid, because of extensive hydrogen bond, this dihedral angle between the planes is decreased, whereas in case of gas there is no possibility of hydrogen gas, so the dihedral angle between the planes increases to 111.5. Now because of this change in the dihedral angle, the bond angle, that is oxygen hydrogen bond angle, also changes. Which one is smaller in case of gaseous phase? Now because of hydrogen bond, this is increases to 101.9. The bond length remains approximately same, that is 1.48 angstrom in case of gaseous phase, 1.46 angstrom, that is approximately same in case of solid phase. Now this is 98.8 picometer, that is OH bond length, which is 95 picometer in case of gas. So this is the comparison between the two structure. So this is what we call as structure of hydrogen peroxide. Now coming to physical properties of this compound, that is hydrogen peroxide, we have these physical properties. So first of all, this is a syrupy liquid whose color is pale blue color, and its taste is bitter taste. So at room temperature, at normal state, hydrogen peroxide exists as a liquid, and that is syrupy. Now this syrupy nature, that means the one having high viscosity. So this syrupy nature of this hydrogen peroxide is again because of hydrogen bond. This nature of this liquid to be syrupy, this is because of hydrogen bond. So hydrogen bond is responsible for the syrupy nature of this molecule, that is hydrogen peroxide. This hydrogen peroxide is soluble in water as well as alcohol. Now when we say a particular substance is soluble in water, the only reason for this compound or the substance to be soluble in water is because of the association of this molecule with water through hydrogen bond. So this hydrogen peroxide can associate with molecules of water through hydrogen bond. Because of the formation of this hydrogen bond, we say that this hydrogen peroxide is completely miscible or soluble in water. Then this hydrogen peroxide, pure sample of hydrogen peroxide is weakly basic, similar to water. So pure water is also a very weakly acidic. Similarly, hydrogen peroxide, if we take a pure sample, This is also a very weakly acidic, means the extent of dissociation will be extremely small. So the quantity of H plus ion produced from this hydrogen peroxide will be extremely small, and hence we said this is a weakly acidic in nature. Now the question is, why this is weakly acidic? Now this hydrogen which is bonded to oxygen in this hydrogen peroxide, this is associated through hydrogen bond with another molecule. Now when this hydrogen is involved in hydrogen bond with another molecules, the tendency for this hydrogen to release H plus ion is extremely small. Because of this hydrogen bond, the extent of dissociation of this OH bond is less, hence this is a very weakly acidic. The same reason goes for water. So water, a pure sample of water is associated through hydrogen bond, and because of this the dissociation of OH bond is very weak, and the acidic nature of the compound or the substance is also very weak. This hydrogen peroxide is a diamagnetic substance. If I say diamagnetic, means when we place this substance in an external magnetic field, this is being repelled. Now the property of this substance to get repelled by an external magnetic field is what they call as diamagnetic, and diamagnetism is due to the complete pairing of electrons in its orbitals. Now we take the help of molecular orbital theory. We have this peroxide ion. Now peroxide ion, if you write the electronic configuration based on molecular orbital theory, each and every orbital has got completely filled orbital. Now since none of this electron is unpaired, so all the electrons are completely paired up according to the molecular orbital theory, these peroxides are diamagnetic in nature. So we have to explain this diamagnetism from molecular orbital theory. Then this hydrogen peroxide, the dielectric constant of this hydrogen peroxide is very high, similar to that of water. Because of this high dielectric constant, this hydrogen peroxide behaves as a very good solvent for electrolysis. That means ionic compounds को dissolve करने के लिए आसानी से dissolve करते हैं. Similar to polar compounds, ionic compounds are very soluble to water. The reason being the high value of dielectric constant of water. Similar to water, this hydrogen peroxide also has got a very high value, a large value of dielectric constant. Because of this acts as a very good solvent for electrolytes. Now this hydrogen peroxide, as we have seen earlier, can exist in gaseous form or as in solid. Now when we take this solid hydrogen peroxide, this melts as 272.4 Kelvin, that is minus 0.7 degrees centigrade. So that means in this solid state, these molecules are associated through hydrogen bond. So we have to break this hydrogen bond. So to break this hydrogen bond, a very small amount of energy is required. That is what we call as low melting point. So melting point is 272.4, that is minus 0.07 degrees centigrade, and this boils at a very high temperature compared to that of water. So under 1 atm, this boils at 423.2 K, that is 150 degrees centigrade. So if you look at this, the boiling point of water and boiling point of hydrogen peroxide, boiling point of hydrogen peroxide is greater than that of water. The reason being, in case of hydrogen peroxide, the extent of hydrogen bond is more compared to that of water. Since the extent of hydrogen bonding is more in case of hydrogen peroxide than in case of water, we say the boiling point of hydrogen peroxide is greater than that of water. Now its density is 1.469 gram per ml, which is again very large compared to that of water. Water at room temperature, that is at 4 degrees centigrade, is density is 1 gram per centimeter cube or 1 gram per ml. So density of water is 1 gram per ml, whereas the density of this hydrogen peroxide is 1.6969 gram per ml. So the larger value of this density, that is high gravity of this hydrogen peroxide, is again because of the association of these hydrogen peroxide molecules through extensive hydrogen bond. So when we compare the hydrogen bond, the extent of hydrogen bond in case of water and in case of hydrogen peroxide, the extent of association of molecules through hydrogen bonding is more in case of hydrogen peroxide. Because of this, its density is more, it is more viscous, that is syrupy liquid. Now, this hydrogen peroxide, the sample of hydrogen peroxide, we have to the strength of this hydrogen peroxide. So, the liquid hydrogen peroxide which is available in market, this is marketed as 30% solution. So, a 30% solution of hydrogen peroxide is marketed as 100 volume. That means this hydrogen peroxide, the concentration of hydrogen peroxide is expressed in terms of a term which is known as volume strength, which I am going to define later on. So, a 30% solution of hydrogen peroxide is marketed as 100 volume hydrogen peroxide. So, that means if I take 1 ml of this hydrogen peroxide, 1 ml of hydrogen peroxide at room temperature or at STP will produce 100 ml of molecular oxygen. So, if I say a sample of hydrogen peroxide is 100 volume, and this 100 volume is corresponding to 30% of the sample. So, concentration is 30%. This is marketed as 100 volume. So, that means 1 volume of hydrogen peroxide at STP will produce 100 ml of molecular oxygen. Commercially, it is marketed as 10 volume. So, if I say 10 volume, the 100 volume is given as 30%, then 10 volume will be considered as a 3%. That means, if I say the strength is 10 volume, that means 1 ml of this hydrogen peroxide will release 10 ml or 1 liter will release 10 liters of molecular oxygen at STP. So, this is what we call as the strength of hydrogen peroxide. Now, we'll define this strength in terms of another quantity which is known as the volume strength. Now, this volume strength of hydrogen peroxide, the volume strength of hydrogen peroxide is defined as the volumes of oxygen gas produced at STP from 1 volume unit of hydrogen peroxide according to this reaction. So, hydrogen peroxide decomposed to give you molecular water and oxygen gas. Now, if I take 1 volume of hydrogen peroxide, then how many volumes of oxygen gas will be produced from this 1 volume unit of hydrogen peroxide at STP, that is known as the volume strength. So, definition says volume strength is defined as volume of oxygen produced at STP condition from 1 volume unit of hydrogen peroxide. So, if I take 1 ml of hydrogen peroxide, how many mLs of oxygen gas will be produced at STP? That is what we call as the volume strength of hydrogen peroxide, which is written as 100 volume or 10 volume. So, this 100 volume, this is nothing but the volume strength of hydrogen peroxide, or this 10 volume is also defined as the volume strength of the hydrogen peroxide, that is the strength or the concentration of hydrogen peroxide. So, definition says how many volumes of oxygen gas will be produced from 1 volume of hydrogen peroxide at STP, that is defined as the volume strength. So, for numerical point of view, this volume strength of hydrogen peroxide is equals to 5.6 times the normality of hydrogen peroxide, or this is 11.2 times molarity of hydrogen peroxide, where this is the concentration. N represents normality, whereas this capital M represents molarity as a unit of concentration. And we know this molarity is related to normality through N factor. Normality is equals to N factor times molarity, and for this hydrogen peroxide, This, according to this reaction, oxygen is changing from -1 to -2, -1 to 0. Now look at this. Each oxygen is changing from -1 to -2. There is a change of 1 unit. So since there are 2, so the total change is 1. So n factor is 2. We can also take this -1 to 0 changes 1, but for 2 oxygen change will be 2 into 1. Again this is 2. So n factor is 2 for this. So therefore normality of hydrogen peroxide is related to this mole fraction molarity as this ratio. So this is what we call as the volume strength. So if we have to define the volume strength from the concentration, then we have to use this relationship. So once we have this concentration, we can easily define volume strength. So this volume strength is defined as the volume of oxygen gas produced at STP from 1 volume unit of hydrogen peroxide. So what we have to keep in mind is commercial sample which is available in market. This is marketed as 10 volume. So 10 volume corresponds to 3%. 10 volume corresponds to 3% hydrogen peroxide. So if I say 10 volume, that means 10 ml of oxygen gas will be produced at STP from 1 ml of hydrogen peroxide. Or if I say 10 liters of oxygen gas will be produced from 1 liter of this hydrogen peroxide sample at STP. That is what we call as the volume strength, which is nothing but the concentration of a sample of hydrogen peroxide which is available in market. Now coming to chemical properties of this compound, that is hydrogen peroxide, a very important and very interesting behavior of this hydrogen peroxide is this hydrogen peroxide can act as an oxidizing agent as well as a reducing agent in acidic, basic or neutral medium. But this is a powerful oxidizing agent but a weaker reducing agent. So this is more commonly used as an oxidizing agent compared to its reducing agent. But otherwise this can function as oxidizing as well as reducing agent. Now coming to some of the important properties of this compound. Stability. When we talk about the stability, now this hydrogen peroxide on standing, it decomposes to give you liquid water and oxygen gas. Now this stability, now since it's decomposing to give you water and oxygen, so we said this is unstable to decomposition. Now this decomposition is catalyzed by sunlight or transition metals present in glass bottles. So to avoid this decomposition, this sample of hydrogen peroxide, this is always stored in plastic colored wax lined bottles, so that the decomposition, the catalyst for decomposition is not available and decomposition is suppressed. If this is stored in glass bottles, the transition metal ions, alkali or alkaline metal ions present in this glass act as a catalyst, and this helps in decomposition of hydrogen peroxide. Or if this is placed in normal bottles, then this can easily absorb light from the atmosphere. Once this light falls on this surface, it can easily decompose. So to avoid this, this is always stored in colored plastic wax lined bottles so that decomposition is suppressed. Second, this hydrogen peroxide is weakly acidic, as we have just discussed. The weakly acidic nature of this hydrogen peroxide is because of the association of these molecules, that is hydrogen which is present in this molecule is associated through hydrogen bond. Because of this association, the extent of dissociation of OH bond is very less. Hence, the quantity of H plus ion present in the solution is also extremely small. Say this is the reason why we say this is weakly acidic. Now look at this. Take this. We take this as sample of hydrogen peroxide. This decomposed to so this dissociates to give you H plus ion and OH minus. Now the constant, dissociation constant, that is 1.5 into 10 power minus 12. Minus 12 is an extremely small value. Since the dissociation constant, tendency for dissociation is extremely small, so the quantity of H plus ion in the solution will also be very small, and we say this is acid, weakly acidic in nature. Now coming to this oxidizing properties. Now the oxidizing property of this hydrogen peroxide is these hydrogen peroxides on decomposition gives you liquid water and nascent oxygen. Nascent oxygen means newborn oxygen, which is very strongly oxidizing. So this nascent oxygen, which is responsible for the oxidizing property of this hydrogen peroxide, now this being a very unstable, it immediately combines with another nascent oxygen and this gives you molecular oxygen. So this was the reason why I gave you molecular oxygen here. So, but initially this is nothing but the nascent oxygen, and this nascent oxygen is responsible for the strong oxidizing property of this hydrogen peroxide. So we have some of the reactions here. So look at this, lead sulfide on reaction with hydrogen peroxide, this is converted into lead sulfate plus water. Now look at this. In this reaction, sulfide, which was initially -2 oxidation, is now is oxidized to +6. So sulfide is oxidized to sulfate. Take this, we have ferrous and iron +2 oxidation is said when this is made to react with hydrogen peroxide in acidic medium. +2 is oxidized to +3. So ferrous iron is oxidized to ferric iron. Now we take this potassium iodide, we have I-. So I- on reaction with hydrogen peroxide, this is oxidized to molecular iodine. So iodine changing from -1 to oxidation 0, that is what we call as the oxidation. Similarly, look at this sodium arsenide, arsenic in +3 is oxidized to +5 when this is made to react with hydrogen peroxide. So this arsenide is oxidized to arsenate ion. Similarly, look at this dichromate, potassium dichromate on reaction with hydrogen peroxide. This is oxidized to give you potassium chromate. Potassium superoxide. Now coming to reducing nature of this hydrogen peroxide. Now we take this potassium permanganate. Potassium permanganate on reaction with hydrogen peroxide in acidic medium. This Mn, initially this was in +7 oxidation state, now this changes to +2, so there is a reduction. So in this reaction, hydrogen peroxide is acting as a reducing agent. In the next reaction, we have reaction of ozone with hydrogen peroxide. Ozone is a much powerful oxidizing agent. So in this reaction, ozone is acting as an oxidizing agent and hydrogen peroxide is acting as a reducing agent. Now this is acting as a reducing agent, so HCl must be oxidized, so this is oxidized to molecular oxygen. Now reaction of HOCl with hydrogen peroxide. Initially Cl was in +1 oxidation state. After reaction with hydrogen peroxide, this is changing into -1. So there is changing from +1 to -1. So we say this is reduction. Now look at this molecular iodine reacts with hydrogen peroxide in alkaline medium or basic medium when iodine is changing from 0 to -1, that is reduction. So molecular iodine can be reduced to iodide by reaction with hydrogen peroxide in alkaline or basic medium. We take this potassium permanganate with hydrogen peroxide. This was an acidic medium when this changes to +2. Now in basic medium this changes to +4. So whether we have this acidic medium or basic medium, this MnO4 is converted into the lower oxidation state by reaction with hydrogen peroxide. So these are some of the properties in which hydrogen peroxide shows oxidizing as well as reducing. Apart from this hydrogen peroxide is also used as a bleaching agent. So the bleaching action of this hydrogen, bleaching is to fade the color को fade करना. Now the bleaching action of hydrogen peroxide is because of this oxidizing character, and this is nothing but the production of this nascent oxygen. This nascent oxygen, which is responsible for oxidizing property, is also responsible for the bleaching agent. Bleaching means color को fade करना. So this is some of the chemical properties in which hydrogen peroxide shows both oxidizing as well as reducing character. And finally, some of the important uses of this compound, that is hydrogen peroxide. So we have some important uses of hydrogen peroxide which I have listed here. In daily life, this is used as hair bleach and as a mild disinfectant, as an antiseptic. This is sold in the market as perhydrol. Now look at this. When you go to the salon for treatment of hair, now there is a particular liquid which is placed in a white color bottle, small size bottle. If you apply this on your hair, this hair color fades and becomes brown color. So that particular liquid which is used on the hair for bleaching, that liquid is hydrogen peroxide. That is what we call as hair bleach. But otherwise, this hydrogen peroxide is a very good antiseptic, and as an antiseptic means when we have some scratch या कुछ scratch हो जाता है तो we apply this hydrogen peroxide as an antiseptic. So this as an antiseptic, this is marketed as perhydrol. Second, this hydrogen peroxide is used as a raw material or as a reagent for manufacturing of large number of chemical compounds. Third, this is used as a bleaching agent for textiles, pulp, leather, oil, fats, etc. And the most important is this is used in environmental chemistry, that is green chemistry, for pollution control treatment of domestic and industrial effluents, means for treatment of wastes. Oxidation of cyanides, respiration of aerobic condition to sewage wash. So means just cleaning up of this sewage or waste treatment, we use this hydrogen peroxide. Then this restores the color of all lead paints blackened by action of hydrogen sulfide. That means now lead containing paints, when this is exposed to atmosphere, then atmosphere contains hydrogen peroxide. This combines with hydrogen peroxide and is converted into lead sulfide, whose color is black. Now to restore the original color of that particular paint, we treat with this hydrogen peroxide when this lead sulfide is oxidized to lead sulfate, which is white color. So now look at this, we have this PBS which is black. This on treatment with hydrogen peroxide, this is converted into lead sulfate. So lead sulfate is white, so the original white color of the substance is restored. So this is some of the important uses of hydrogen peroxide. So this is a brief discussion about this very important compound of hydrogen, that is hydrogen peroxide.